All right, so this is starting chapter 10. Chapter 10 kind of jumps all over the place, but it's more specifically about using derivatives and integrals, but using them in different types of applications than we've used before, such as this section we're talking about parametric functions. Now we've talked about parametric functions in the past. Way back in chapter 1 we talked about what a parametric function was. And then in chapter 4, I think it was, we talked about how to find the slope of a parametric function by doing dy dt over dx dt. And part of that was just to see how when you multiply derivatives with the power rule or with the chain rule, things can cancel out and it can convert a function or a derivative into a derivative of some other type. But we're going to get a little more involved in it here. Remember, parametric functions are just functions that are defining x and y separately with separate equations, and both of those equations are going to be in terms of some parameter that typically is going to be t. All right, so way back in chapter 1, as I mentioned, we talked about parametric equations. Parametric equations can be used to describe motion that's not a function. But this x one would be a function of t, and the y one would also be a different function of t. So you can define it as two equations that are each functions of t, that parameter we were talking about, while just looking at the graph, hopefully you can recognize right here that that is not going to pass the vertical line test to be a function. But we can treat it like this, and our derivatives and things can still work out. Now, if f and g have derivatives at t, then the parametrized, hard to say there, curve also has a derivative at t. And this part we've kind of talked about already. The formula for finding the slope of a parametrized curve is dy dx equals dy dt over dx dt. So you take the derivative of the y equation with respect to t and divide it by the derivative of the x equation with respect to t. Now this makes sense when we think about canceling dt, because if we can assume that the denominator is not 0, well, what we can do there is, remember, when we're dividing fractions, dy dt, keep, change, and then flip dt dx, and then the dt's would cancel out, leaving you with dy dx, which is nothing more than slope, the change in y over the change in x. So that's how this works. All right, now to find the second derivative of the parametrized curve, we find the derivative of the first derivative. So d squared y over dx squared, we're going to take the derivative with respect to x of y prime. And that is nothing more than the derivative of y prime with respect to t over dx dt. Now notice this one down here does not have a second prime. Up here we're taking the derivative of the derivative of y. Down here we're just taking the derivative of the original x. So find the first derivative, find the derivative of dy dx with respect to t, and divide by dx dt. All right, now for an example here, find d squared y over dx squared as a function of t if x equals t minus t squared and y equals t minus t cubed. All right, so first things first, we're going to want to find what dy dx is. So remember, for dy dx, that's dy dt over dx dt. And let's go ahead and find the dx dt and the dy dt. So dx dt, that's dx, is going to equal 1 minus 2t. And then dy dt is going to be 1 minus 3t squared. So here we would end up with 1 minus 3t squared over 1 minus 2t. And that's going to be the first derivative. Now, to find the second derivative, we're going to go ahead and take the derivative of this with respect to t. So we're going to find, so this is y prime. So we're going to find the derivative of y prime with respect to t again. And that we're going to have to use the quotient rule for. So bottom, 1 minus 2t times the derivative of the top, which is going to be negative 6t, minus top, 1 minus 3t squared. Ooh, that's an ugly dog. Squared. Times the bottom, or sorry, the derivative of the bottom, so negative 2, all over the bottom squared, 1 minus 2t, quantity squared. All right, so when we distribute here, we're going to get negative 6t plus 12t squared. Distribute this minus through to the 2, and that means that these are going to be plus. So we get 2 times 1 gives me plus 2. And then 2 times the negative 3t squared gives me minus 6t squared, all over 1 minus 2t quantity squared. All right, and then we can combine like terms and simplify here. We got 12t squared minus 6t squared, so that's going to give us 6t squared minus 6t plus 2 over 1 minus 2t quantity squared. Now, that is just dy prime dt. We want the second derivative, and that means we're going to have d squared y over dx squared, and that is dy prime over dt divided by dx dt. Now we've already found dx dt. We found it up here. It's 1 minus 2t. So that means we're going to use this, d 6t squared minus 6t plus 2 over 1 minus 2t quantity squared divided by 1 minus 2t. So we're going to end up with 6t squared minus 6t plus 2, and then we divide this. That means that's just going to increase that by 1 power, 1 minus 2t squared. Whoop, cubed. Cubed, 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 cubed. All right, so there's the second derivative. And what that's doing is that's telling us where it, the same way we would always do, use the second derivative with respect to x. It'll tell us where this thing's concave up, concave down, and all that stuff if you want to break that down. Same thing with your dy dx. When you find this right here, that's going to tell you where that thing is increasing, decreasing, where this is equal is going to be possible critical points, where you might have a maximum or a minimum and all that stuff. All the things that you've done with the derivative up to this point are still going to be true. We're just finding them a little differently because the function is defined a little bit differently. All right, now also you're going to have to use calculus to find the length of a parametrized curve. And the equation for that is similar to our previous length of curve equation that we had. Remember, this is the length of the curve equation. Well, actually, this is the length of the curve equation for the parametrized curve. dx dt quantity squared, dy dt quantity squared, and you're doing the square root. Integrating from a to b, the beginning value of t. Remember, this right here tells you what your bounds are in. So these bounds are in t values, not x's or not y's. So this is going from t equals A to t equals B. And that'll be the length of this equation, of this curve. Now you can also notice the use of the Pythagorean theorem. X value, y value, squared squared plus, and that's going to give you the length of it. Alright, likewise the equations for surface area of a parametrized curve are similar to our previous surface area equations. Guys, these are good to know for the future. You will not be asked that on an AP exam. That's not, if they ask you anything about that, they're going to give you that equation. Alright, so here's it's 2 pi y, there's your circumference right there, and then the circumference, and then this is going to be the length, and then you're just adding all that together, all those little slices, which is nothing more than a circle rotating around this thing, so that's going to be the sum of all that, which is going to give you the surface area. Same thing with this one, except you've got 2 pi x, which is going to be the surface wrapped around the x-axis. Alright, this curve right here is t plus sine 2t, and y of t is t plus 2 cosine 5t. Just to give you an idea of how complicated things can be. Remember, your x is based on t, your y is based on t. The way you form one of these things, you just have to do it over and over and over again, but we'll say like when t is 0. If t is 0, what is 0 plus sine of 0? Well, that's 0 plus 0, which is 0. And here, what's 0 plus 2 times the cosine of 5 times 0? 5 times 0 is 0. Cosine of 0 is 1. So we end up with 0 plus 2 times 1, which is 2. And there's your point 0.02 right there. And you would do the same thing for when t is 1, t is 2, t is 3, t is negative 5, all the values that you've defined this thing for. In this case, your domain are t values, not x values, because the domain are the values that you're putting into the function, and we're putting in t values. So you just t equals 1, t equals 2, t equals 3, t equals 4, and that can give you some points to actually find out about where you're going to go. But that's how the calculator graphs this thing. It does it for little bitty steps of t and calculates all those points. Alright, that's all the introduction. That's pretty much all there is for parametric equations. Just remember, it's basic stuff. It's not super complicated.